Welcome back to The Explainer. Today, we're setting the stage for a seriously high-stakes detective story. And get this, it takes place entirely inside the thick steel hull of a massive ship. You know, when a 100,000-ton vessel is out there just battling the violent forces of the ocean, the structural integrity of its welds is quite literally the difference between life and death.
So picture this. An inspector places this small, pretty unassuming probe right on a freshly finished weld surface. On a nearby screen, a pulse echo trace just jumps to life. And then, suddenly, a massive spike appears at a completely unexpected depth on the graph, exactly 12 millimeters below that solid surface. A fatal crack is just lying there, hidden in the steel.
Invisible to the naked eye, highly dangerous to a vessel under load. And yet, boom, it was found. How? Well, through ultrasonic testing, or UT for short. This is absolutely the ultimate detective tool. It's the single most sensitive volumetric inspection method available to a shipbuilder today. It spots the critical defects that other methods like radiography, for example, just completely miss. And the craziest part, it literally does it using nothing but sound. Okay, let's dive right into Section 1, the physics of ultrasonic testing, using sound as an investigative probe.
So let's walk through this pulse echo process together. It all starts with what we call a piezoelectric transducer. Now, this remarkable little device takes electrical pulses and actually converts them into high-frequency sound waves. The transducer shoots this pulse straight into the steel. The wave travels through the metal, and when it hits a discontinuity, like a flaw in the steel, a portion of that energy reflects right back to the transducer. By just measuring the exact time of that round trip, we can calculate the precise depth of the defect. It's pretty brilliant.
And when we talk about travel time here, we are dealing with some seriously staggering speeds. These ultrasonic waves are racing through the ship's steel at approximately 5,900 meters per second. That is incredibly fast. So, the absolutely crucial point here is that these waves, which typically operate at a frequency of about 2 to 10 megahertz, act almost like an incredibly fast acoustic radar. They penetrate the metal until they hit something that definitely shouldn't be there, like a crack, a void, or a bad fusion boundary. Because we know the exact speed the sound travels through the steel, simply timing the echo tells the inspector exactly how deep that reflector is buried.
Moving right along to Section 2, catching what X-rays miss, the invisible enemy.
Now, the enemy I'm talking about here is the tight planar crack. A planar crack has essentially zero thickness. It's practically two-dimensional. Now, think about radiographic testing, or X-rays. If an X-ray beam passes through the steel completely parallel to that crack face, there's almost no change in the material's density. And since X-rays rely entirely on density changes to cast a shadow on the film, that crack is completely invisible on an X-ray image. No way to see it. But an ultrasound beam, it tackles the problem from a totally different angle. It hits the crack perpendicularly. And this comparison perfectly illustrates the difference. Look at the beam direction. Radiography is parallel, making those tight cracks invisible because there's just no density contrast. But ultrasonic testing sends its beam perpendicular to the crack face. Because it's relying on a strong sound reflection rather than a density change, the flaw shows up as a sharp, undeniable spike right on the inspector's A-scan, which, by the way, is just the standard one-dimensional graph readout on their screen. The crack acts like a mirror. I love this quote because it is the absolute perfect analogy for grasping why UT is just so powerful. Think about it. Just as light bounces off a mirror right back to your eyes, the high-frequency sound wave hits the flat face of that microscopic crack and bounces a super strong reflection directly back to the probe. This right here is exactly why UT is the overwhelmingly preferred method for detecting fatal planar cracks in structural ship welds. Let's jump to Section 3, Phased Array Technology, the modern upgrade. So conventional UT requires an operator to literally manually slide the probe back and forth, interpreting multiple single-line graphs along the way. Honestly, it's incredibly time-consuming and heavily dependent on the operator's individual skill. But phased array UT, it changes the game entirely. It uses a multi-element probe. Instead of physically moving the probe to change the angle, advanced electronic timing controls fire the elements in rapid sequences to steer and focus the beam electronically. It's like magic, but it's just really good engineering. Notice the sheer amount of data being generated here? Instead of just a single spike on a graph, phased array produces a real-time sectorial scan. It's basically a 2D color-coded slice right through the weld cross-section. It shows all the reflectors simultaneously. Because it's faster, far more reliable, and actually creates a permanent digital record that engineers can review later, phased array is increasingly becoming the absolute standard diagnostic method in modern shipyards.
Finally, let's wrap up with Section 4, the final verdict, securing the ship's integrity.
All right, so here are your core takeaways from this explainer. Ultrasonic testing leverages high-frequency sound to image the deep interiors of welds. It is virtually unparalleled at finding the tight, zero-thickness planar cracks that X-rays simply cannot see. With modern phased array technology, we get these brilliant, real-time 2D images in a single pass. And because of this completely unmatched accuracy, UT is absolutely mandatory on all fatigue and pressure-critical joints across a ship's hull. No exceptions.
Now, sound waves are incredible at probing the deep interior of the metal, for sure. But this leaves us with a really interesting question. What about the incredibly fine near-surface cracks? You know, the ones that are too small for the human eye during a visual inspection, but not deep enough to warrant a full ultrasonic scan. How on earth do we find those? Well, catching those requires a completely different kind of physics, and it perfectly sets the stage for our next explainer on magnetic particle testing. Thanks so much for joining me, and keep learning.